Hello and welcome. The lesson in this video will cover p-integrals. P-integrals are a type of type 1 improper integrals, and our question will always be whether or not they're convergent. The convergence of p-integrals is intimately related with convergence of p-series, so the information in this lesson will become very important once we start talking about infinite series and p-series in particular. So let's get started with our discussion on p-integrals. So as I said, a p-integral is just a particular kind of type 1 improper integral. Specifically, it's the type 1 improper integral integrating from 1 to positive infinity, the function 1 over x to the power p. Now p can be any real number here. It can be positive, negative, 0, whatever you want, just a real number. So for the purposes of integration, I'm going to rewrite the integrand as x to the minus p. Okay, and the way that we understand this type 1 improper integral is we do definite integrals from 1 to t being some positive parameter, and then we're going to evaluate these definite integrals and then take the limit as t goes to plus infinity, and that will be the value of our improper integral. And so the question here is always whether or not that limit exists. Is it convergent or is it divergent? Right? Convergent being the limit exists and is finite, divergent being, well, it blows up to positive infinity, or, it oscillates between some values and doesn't have a limit. Okay, so what we need to do is consider these definite integrals here, integrating from 1 to t x to the minus p power. Okay, and there are two cases here. One for when the power is equal to -1, because we know that case works fundamentally different than any other power sitting here. So if we're looking at the case p is equal to 1, we're integrating the function 1 over x in that case, and we know that this has the antiderivative natural log of absolute value of x. So then we just need to evaluate natural log of absolute value of x at t and at 1. T is positive here, so I can drop the absolute values, they're redundant. And the natural log of 1 is 0. So no use in writing minus 0. So the value of our definite integral here is just equal to natural log of t. And now we're always just going to ask this question of what is the limit as t goes to plus infinity, because this will be the value of our improper integral, our p-integral. And so in this case, we're asking what is the limit of natural log of t, because this is our definite integral. And of course, as t goes to plus infinity, natural log of t blows up. This goes to positive infinity. Okay, so we have divergence in the case when p is equal to 1. Okay, so that's our first case, p is equal to 1. So what about all other values of p? So for any other value of p not equal to 1, this integral can be computed using the power rule. And so we'll have the definite integral from 1 to t of x to the minus p with respect to x. I can compute this value by finding the antiderivative just being x to that power plus 1, and then I divide by the new power, so I have 1 over 1 minus p times x to the 1 minus p power. So added 1 to the power and then divided by whatever I saw in the power. And then I need to evaluate at 1 and at t and then take the appropriate difference. So evaluating at t, I just get t to the 1 minus p. Evaluating at 1, I get 1 to the 1 minus p, but of course 1 to any power is just equal to 1. And then I have this common factor of 1 over 1 minus p, which I pull to the front. Okay, and now the question is always just going to be, what is the limit of this expression? But if you think about it, 1 over 1 minus p has no dependence on t. T to the 1 minus p definitely has dependence on t. And 1 has no dependence on t. So taking a limit of this entire value is going to come down to taking a limit of just this term, t to the 1 minus p. So we want the limit of the whole expression, but really we only need to take the limit of t to the 1 minus p. And so there are two cases here. One case is going to come from when p is strictly greater than 1, because that will make our power here 1 minus p, that full exponent, it will make that equal to a negative number, right? And so if our exponent is negative, then this limit will just be equal to 0. And in the other case, so we'll have convergence in that case, which I'll write in a second. And if we consider the case where p is less than 1 strictly, now we're looking at t raised to the power 1 minus a number less than 1. So 1 minus a number less than 1 is positive. So t to a positive exponent, this is going to blow up with t. It goes to positive infinity. So we'll have divergence in that case, convergence in this case. Okay, and I'll write all of this down and summarize everything that we just did. So what we just saw is that the p integral from 1 to plus infinity of the function 1 over x to the p converges for values of p that are strictly greater than 1 and diverges for all other values of p. In other words, it converges for p strictly greater than 1 and it diverges for p less than or equal to 1. And then furthermore, in the case of convergence, when p is strictly greater than 1, we can compute the value of this integral. Not only do we know that the value exists, we can actually compute what it is, and it depends on p, which shouldn't be all that surprising. But either way, this has the value. Well, what we just saw was that it's the limit of that quantity 1 over 1 minus p times t to the power 1 minus p, which goes to 0 in the limit, and then we subtract 1, so it'll just go to 1 over 1 minus p times 0 minus 1, right? We got this from taking our limit, but now this is just negative 1 times the quantity 1 over 1 minus p, and this just turns out to be 1 over p minus 1. And I'll just erase that and write it nicely. So this is very important for what we'll do with p-series in the future. The convergence of these p integrals is intimately tied with the convergence of p-series, and so that'll be a very important question, and it'll be very nice to have an answer to it in the future. And then also the value for this p integral for these convergent values of p, this will provide us with information on upper bounds for p-series, which we'll discuss further in that lesson. So that's it for the lesson on p integrals. I hope you found this helpful. Please leave comments in the comment section, feedback, any kind of constructive criticism that you may have. And thank you very much for watching. I hope you tune in again.